Hello, and welcome to the Satellite Image Deep Learning Podcast. In this episode, I catch up with Gilberto Camara to talk about SITS. SITS is an open-source R package for land use and land cover classification of big Earth observation data using satellite image time series. Gilberto is a senior researcher in GIS science, Geoinformatics, spatial data science, and land use change at Brazil's National Institute for Space Research. I give you Gilberto. Hi, Gilberto. Okay. Welcome to the podcast. How are you?
Thank you very much, Robin. It's a pleasure to meet you, and congratulations on your nice work and making people aware of whatever techniques, methods are available for image processing now in Earth observation.
Thank you so much. It's a pleasure to be able to provide that service. And yourself, you are the author or one of the lead authors on the SITS package. Do you mind giving us a quick introduction to that?
Yeah. Well, I'm a bit of old timer in Earth observation, being around the place for 40 odd years. So I've seen, at the time when there was only Landsat, and each Landsat image cost $1,000. So to cut a long story short, I've been quite involved in opening the data and open software. And I was director of the Secretariat of the Group on Earth Observation in Geneva, and also before that, director of the National Institute of Space Research in Brazil, which has one important task, which is monitoring deforestation in the Amazon using remote sensing data.
Right, and that's obviously a time series task.
Yeah, it's a time series task. So I think the turning point came very late in the game, when actually the players decided to make their data available, which was like Brazil was the first in 2005, and then US Landsat in 2008, and then the Commission with Sentinels in 2012. Now, there was this first wave of making data available. And the second wave actually was launched by Google, I would argue, when they said, okay, let's put all the data together and provide means of exploring the data. And the Google Earth Engine came into being. So now you had 2 + 2, you had open data in a massive scale, and Copernicus and Continuation, Landsat, other satellites from the United States, and go on, and satellites from Brazil. And then you have now the emergence of cloud services, which include Google, but also include the Copernicus services, Amazon, and Microsoft, which say, okay, the data is there. Then the third link in the chain is the software. Okay, so you should be able to write software to explore the possibilities of the data which is there. Now, when Google started, they were constrained, and they still are constrained, by the commitments, of course, of the company. I mean, they are out to make a profit. And the first thing they had was, you have to realize that Google Earth Engine had to be designed around the other applications in Google, which use this MapReduce approach. And which is massively parallel, like search is a massive parallel organization. I remember because I was invited by Google in a sort of think tank meeting, which they started the design of Google Earth Engine. And I remember being told that, everything we have to do, we can do, but it has to fit the MapReduce paradigm.
Right.
Which means that you have to take a decision. And the decision Google took was to cut the images in space. In space, each image is cut in chunks, and each chunk is allocated to a machine. And therefore, it means that anything you do that can be broken down to this pyramid, the spatial pyramid, will run extremely fast. So anything that depends on pixels and pixels without time will run extremely fast. And then they had a very good designer, Noah Gorelick, which designed the Google Earth Engine, the first version, which is JavaScript. And they designed it very well. So they had a paradigm of simple things, which are the ones that are important. They had this paradigm of image collection. And they had the notion of algorithms that apply to image collection, functions that are applied to image collections, not only to images, but to collections, and filters in space and time that you could apply to the collections.
Mm-hmm.
Okay, and then Google essentially had this, and it was and is a major milestone in Earth observation. Now, then two things happen. They are constrained by the structure, the underlying MapReduce structure of Google, which anything that's not pixel-wise massively parallel will not work well, or work only in selected, very small examples. Mm-hmm. The other thing is Google AI and Google Colab came as commercial products. And therefore, they were constrained in the way that they could put algorithms from deep learning and AI proper in the machine, in the Google Earth Engine. So essentially, if you look from where I sit, it is an excellent product frozen in time. Now, and then came, of course, first Amazon, then Microsoft, and more recently, the European Commission. So what they realized was, okay, I cannot foresee in advance what are going to be the developments that are going to happen in machine learning for Earth observation. It is very hard to keep up with new developments that are coming time after time, and people are innovating time and time again. So what I'm going to do, and that is, I would argue, Microsoft did this very well, and they invested on it. I think Microsoft is the competitor to Google with the planetary computing. What they said, we're going to give you virtual machines, either for free, if you want a medium-sized virtual machine, or for to charge if you want to pay. Then we're going to give you free access to your data and efficient access to your data, which basically came in with the investment of the so-called stack protocol. Mm-hmm. So the stack protocol essentially gave users the ability to browse through the entire collection of what is in the cloud, Microsoft or Copernicus or whatnot, and then organize the data for their own purposes. Now, that's the stage we're in. You either have Google, which is essentially a frozen product in time, very good for processing single images or images which are averages, or you're back to Microsoft or Copernicus, where essentially you need to have something that works for you. Now, what happens in 90%, 95% of the cases? Well, people would say, well, I know some Python. I'm going to write an algorithm that solves my problem. And they go there, write a Python script, do some things, keep up with pandas, come up with some deep learning package, or write their own, come up and publish some paper or publish some application. And of course, the result of this is that you get a huge fragmentation. No one talks to no one because it's not a system. What we did in SITS, and we have to say that we benefited from the fact that we looked very closely at what Google Earth Engine is doing, and also because we have a very strong background on applications for deforestation, tropical agriculture, cities management, and so on. And we say, okay, but we need to imagine a user. So can we give users a similar experience as they have on Google Earth Engine, a very neat and clean API, which hides all unnecessary details and does the work for them. And this is the basis for SITS. And again, can we try to avoid direct competition with Google Earth Engine? It does not make sense to make another Google Earth Engine run on Microsoft Planetary Computing. So you have to say, okay, I'm going to do what cannot be done in Google, because it's done in Google. You do it in Google, come on. You don't underestimate the quality and the ability to learn. So we said, okay, let's concentrate on the time series. And when I mean time series, I mean time series. I do not mean one image and the second image where you compare the two. I mean a time series that takes as instances in time, and where instead of classifying one image, you classify what we call time first, space later. You first classify the time series, as you do, for example, in applications in financing. In financing, you have time series of for example, shares on the stock exchange. So you have a time series of a share, Microsoft, Amazon, whatever, Facebook. And then you process the time series. What's the deal with that? The hope is you don't lose any data.
Mm-hmm.
When you go to Google and you say, I want the Landsat collection for year 2010, 2012, the first thing Google asks you, I do a summary of that data. You do the best or the average of the median image. Immediately, you throw time out of the window. And you throw time out of the window because the now pixels, which are the average pixels, they come from different dates of the year. So you lose the difference between the dry season and the wet season. If you take the time series, what you're aiming at, you take as much of the data collected by the satellites as you wish. So if you have Planet, you have a bi-monthly or monthly time series. If you have Sentinels, you may have a bi-monthly time series. If you have satellites with more, let's say, increased temporal availability, you can break a time series at a reasonable scale. Typically, we're using 15 days. We could use 10. Some people that I know from Planet use 15 days. So you have one data every 15 days, and you interpolate when you have clouds. And then you classify the time series. And then later on, we do the space later. We do some post-processing to harmonize the space. And we try to do this completely hiding all parallel processing problems, all problems that have to do with, for example, the tuning of deep learning algorithms. So if you take a transformer algorithm, you would expect that the first thing a user would do is say, train this data using a transformer algorithm, find out what the reasonable defaults are. Or if you want to do tuning, we can do tuning for you. But if you just want to see what is the output of a transformer, here it is, minimal API. So the idea is a minimalistic API, which helps users, not programmers, and I think that's important, helps scientists get the job done. And so this was the aim, was to reach people who have problems that cannot be solved by Google.
Yeah. That's really interesting. So is the workflow that I would extract a data cube from Earth Engine or Stack Catalog, then load it into an environment?
You build a data cube, to be more correct, because the catalog from Landsat or Sentinel has gaps, because Sentinel-2 and 2A have gaps. So you build a data cube out of a region in space and time, 1 million square kilometers, for example, and then you process that data. And you lose as little data as possible. And then you have functions to cleaning up your training data, accuracy assessment, validation, uncertainty measurement, ensemble predictions, analyzing your result, getting your data best. So it's really user-centered. If you want to add an algorithm, you can, but the idea is not to be, we take a look very carefully at what algorithms are there. We see which have a potential for becoming really operational in terms of what the user would do. We look very carefully at the literature, and then we try to put them into ways that can be usable. Because if you have looked very carefully at the deep learning literature for images, and I wouldn't say every, but most of the published GitHub code that deals with deep learning, especially image type series, are being scrubbed, looking, talking to the others, seeing what works, what only works in the paper, who might work in practice, and so on. And of course, things like, for example, optimizing for GPU is completely under the hood. The user just say, doesn't even know if the machine has a GPU, it's optimized for the GPU. You don't want the user to be burdened. For example, what do I do if I have 64 cores? We handle it for you.
Mm.
What do we do if you don't have to start writing parallel processing code? So, and this led to a very crucial decision for us, which is if you're doing user-centered deep learning, do you do it in Python or do you do it in R?
That's actually a question I did want to ask, the decision was behind the choice.
The decision was behind R for the reason that you don't write such a big package without lots of other packages that you can rely on. Okay. You don't do it yourself. I mean, 90% of the code is not ours, is on packages that the equivalent of pandas, which is SF, the equivalent of torch, there's a torch in R. There is the equivalent, for example, for parallel processing, or for example, for coding things in C++. And the difference is we know who the authors of these packages are.
Right.
We can talk to them. We are friends. We rely on them. We work with each other. And therefore, we have to ensure a level of reliability. Because sometimes the problem might occur, and very frankly, it occurs in our code. But sometimes it is on the code that you rely upon. And you have to talk to the guy who did that problem and ask him if he can fix that bug. And because it's not an algorithm, it's a full user package. I doubt, I'm not saying it can't, I doubt that a package such as SITS, which is comprehensive end-to-end, could today be done in Python. Because Python does not have a CRUN. You know what CRUN is for R, which is the repository where you have to deposit your packages. And it's very stringent on the rules that the package has to deal to get there. So there's a set of tools developed by RStudio, which I don't think there's an equivalent in Python for manipulating tables, manipulating data structures. It's called a tidyverse. I haven't seen anything close in Python. And when you deal with a lot of data structures, for example, you deal a lot of not only raster data, but metadata about the raster data, or metadata about the training data. You need to have packages who can manipulate metadata efficiently and select anything that you want, either on space or time or an attribute. You need that. And you have that in R. Although that the decision in that sense was because we considered, we hope, and we very much hope, that something like SITS will eventually exist in Python. For the moment, it doesn't. I have not seen anything close to it. I've seen a lot of algorithms, a lot of nice things, a lot of nice demonstrations. But something, for example, we have two big ecosystems in Brazil. One is the Amazon forest. It's 4 million square kilometers, bigger than Europe. Okay. The other one is the Cerrado, which is savannas, similar to the African savannas, if you know Tanzania or Kenya, 2 million square kilometers. And we had a team that was using Sentinel data to do land use classification for 2020 for both. So we're talking about 1.5 Europe. And that was done with SITS.
So when you were talking about originally we decided to use R, you're talking about an organization within Brazil?
Well, it's me. I'm the leader, but we have a lot of support from the National Institute of Space Research team, many of which I was the director. Many of the people have been my former PhD students, and there's still technicians there. So it's not Gilberto, myself. I have a team, and we take decisions collectively, including consulting with the other people who do our spatial packages. So it's in a certain sense, for example, we do a lot of, we ask questions to them, they ask questions to us, we meet and we show. There's a sense, R has a sense of community, which does not, to my knowledge, exist in Python. Python is a set of isolated individuals doing very nice work, but very few communities like we have in R, which people work together. When I mean we, there are two we's. There's we Brazil, who developed the package. The users of this package, many of them currently are in Brazil. But also there's the R Spatial community, who we use a lot of their software. And if we use a lot of their software, we have both to communicate with them and to work with them. So that's, in a nutshell, that's the motivation for SITS. We wanted very much to be something that would be useful in operational environments. I mean, when we're talking about classifying 1.5 times Europe with reliability and quality, you're not talking about your average paper from a PhD student.
No.
You're talking about reliability and quality at an operational scale.
That's a good. So my next question is, let's say I want to do that, right? I want to use SITS and process like almost an entire continent for classifying different types of tree cover, for example. How do I do that with SITS?
Well, the first thing, of course, you have to know the field, because SITS doesn't invent training data for you. The SITS is an open source package. It has a lot of documentation available. We try to keep the documentation updated. It's I'll send you the site. You probably have it. I think I sent you in another message. But it is, and of course, we do offer support in the same sense that people from, if you have an issue, you complain on GitHub, and we try to fix it as fast as we can. Sometimes we say, oh, what you're asking, it takes some time. Oh, what you're asking has been solved there. Or what you're asking, we're going to solve and solve your problem. And that's how the community works. I mean, I don't get paid by doing SITS. I'm a retired researcher, and I get paid by consultancy fees and so on, and my retirement salary. But SITS is not a source of income to me. It's a source of duty. I do it because I know that people need it. But we've seen applications using Planet, with Sentinel, with Landsat, in big areas. We will not tell you it works every time. And the most important, hardest thing, by far, is understanding remote sensing. Why am I telling this? As you know, you come from physics, okay? So you know all about remote sensing, because everything in remote sensing has to do with optics of reflectance of the field or response of the field. And the deal is, when we pick an image and we try to classify or to give forest types, you normally, paradigm of 40 years of remote sensing is look at an image, train pixels there, and give it to the classifier and let Google tell you what's similar. If you have a time series, you don't have that luxury. You have a harder task. What is the behavior of that land cover in the dry season? Because an area which is bare on the dry season, in the wet season can be a wetland, it can be a cropland, it can be just another set of bare soil, which was there during the wet season. So you cannot think of a single image as providing you the information you need to train a time series. You actually need to understand the flow of the ecosystem, which for me, as a researcher, is the nicest thing of all. It forces you back to where remote sensing should have been in the very beginning, understanding the physical response of the ecosystems to the signals, either light or radar or what have you, in time, which we lost.
Yeah, I think that's a really good point, to be honest. Like, so much focused on single image features within a single image, but actually the time series often gives that much richer information for remote sensing applications. One final question on, I guess, the implementation side. If somebody's published a new kind of time series model using another framework, Python, JAX, any of those ones, how would they get it into SITS? Is there like a universal language you translate into and then go back?
Well, I mean,
does it not matter?
The current situation is the following. We had to opt for a deep learning library to support. We chose Torch for the obvious reason that many of the deep learning people in Earth observation use PyTorch. And essentially, Torch in R is PyTorch in Python. So if your code is clean, which is not always the case, translating it into RTorch is relatively easy. If your code is not clean, we're not going to need to work together. Yeah. Not every code is clean. But the translation from PyTorch to Torch in R is relatively straightforward. We've done it more. The deep learning algorithms, the transformer algorithm that we run on SITS are actually PyTorch implementations, which we had support from some of the researchers in the field to just understand the algorithm. Sometimes it's not obvious to understand what the guy is doing. But once we understand the algorithm, making the conversion is easy. Yeah. So I would encourage anyone who has a nice PyTorch algorithm that wants to try in SITS, talk to us. And we're very much willing to sit with the guy, translate it into R, and even translate from TensorFlow. I know TensorFlow. I worked with Keras, and we can more or less get most of the equivalents in Keras and Torch, and it's not, big of a deal in terms of the algorithms which I've seen published. So it's not like automatic, but the fact that Torch and PyTorch are de rigueur as most of the algorithms makes the translation relatively feasible. Mm-hmm. So, anyone wants to test the algorithm, talk to us.
Fantastic. Well, that's a really good call to action. And I'm really looking forward to diving into SITS in more detail.
Well, it'd be my pleasure. It will be anything we can do.
Fantastic.
But again, I think you're doing a very important job there's so much things which are scattered around the place that anyone who takes the time and trouble of making pointers. I've looked at your blog posts and I've seen pointers to things which are interesting. The guy from the Imperial College, I was looking at his interview the other day and I said, okay, this is interesting. Let me look at the paper. Let me look at what he's doing and let's see what it's very useful. Very, very useful.
Thank you. And I also hope that this video will help to raise the level of profile SITS has as well. And if people want to follow along the package, the people working on the package, should they follow yourself or is there an official account for it?
Well, they can obviously post on GitHub, the GitHub webpage, which I'm giving the account with issues. They can contact me directly. This is my email. Mm-hmm. So you can share my email with the others. You can contact me by Twitter as well. I'm at Twitter. So and I post sometimes things. So there's various ways of contacting me, either Twitter or email or the package.
Awesome. Well, thank you for that. I'll put all the details in the show notes. But until next time, thanks again.
Thank you very much, Robin, and congratulations on your new job. Hope it goes well.
Thank you. Okay, then.